I am Ricard Burrey. I am working in case department of VSC. This morning, I think Mariano came here. He's working in the same department. Initially, I was told that most of people don't have background on HPC here, but then I'm not sure about this. How many of you already know about supercomputers, HPC in general? Few of you. Well, what I will give is a background, general overview of what is HPC for us in the context of computational mechanics, and how we use it to carry out simulations. So this presentation is about parallel algorithms for computational mechanics. When I say parallel algorithms, it's on the supercomputer scale, right? Okay. So what I will give is a general overview of HPC, methodologies, supercomputers, limitations, walls, and also I will introduce information of Analia. Did you? I guess Mariano gave you some information about Analia code this morning. So I will explain how we use or how we relate with the HPC trends, how we implement them on Analia to carry out simulations on supercomputers. So first of all, I will give a general introduction on HPC trends, and I will interleave this general information, theoretical information, with information from Alia. There are many of these slides that I will present have information from other authors. In some cases, I just copy slides from other authors. So I put a list here of authors from whom I have been copying the information. And well, just for starting, prompted by the exponential growth of computing power, simulation is becoming like the third pillar of science. So historically, science is based on theory and experiments to validate the theory. And we also, more and more, we are using simulations due to the increased capability of supercomputers to perform detailed simulations, right? And we work on this. We work on simulations on computational mechanics context. The units of measure that we use, well, to measure performance of supercomputers is measured in terms of flops, so floating point operations per second, flops. Then the data that is moved is counted in bytes. We have 8 bits is 1 byte, and one double precision unknown, it's 8 bytes. And we use all the time prefixes, mega, giga, tera. The largest supercomputer in the world can perform 125 petaflops per second. This is 10 to the 15 floating point operations per second, right? It has 10.6 millions of cores, and it consumes 15 megawatts, which is around $15 million per year on energy consumption. A laptop nowadays has a performance of approximately 1 teraflop, and the storage generally is in terabytes, gigabytes. Yeah. Okay. The Moore's law is the trend that is following the computing industry for around 50 years, more or less. This is not a law. This is an observation that Gordon Moore from Intel did in the 60s, saying that the density of transistors on computer chips doubles approximately every 2 years, right? In the equivalent in HPC, this means that the performance of supercomputers measured in flops, in floating point in floating point operations per second, doubles approximately every 2 years, right? So every 2 years we have a supercomputer that can perform double the number of operations that can perform per second. This is illustrated here, this trend. And well, this trend is based on some measurements, and these measurements are based on a benchmark. And the benchmark that is used is Limpak benchmark. Limpak benchmark is a benchmark based on operations of linear algebra between dense matrices. Okay, Limpak benchmark is mainly based on multiplication of two dense matrices. So we see that the trend is more or less following the Moore's law, the potential law. This is the first supercomputer in the world. This plot here. This is the number 500, and this is the summation of the first 500 supercomputers. When we see a plateau, it means that the first supercomputer has kept in the top for different periods. Each point is for 6 months, right? So now, for instance, this graphic is from 2016. It's a little old, but the top supercomputer was in there for 2 years, right? If we consider a laptop today that could have more or less a performance of 1 teraflop, it's more or less equivalent to the top supercomputer on the 2000s. So more or less, you have the same power in your laptop than the number 1 supercomputer in 2000.
Small Cray machine.
Hmm?
A small Cray machine.
I don't know exactly which one was, but probably Cray machine. Yeah. So this is the trend that is following supercomputing. We need to unlocking this potential. Increasing potential is not trivial. We need to work in order to adapt our codes in order to achieve or to unlock all this performance. Here we see the last list. You can check in top500.org. And nowadays, the number 1 supercomputer is from China, Sunway supercomputer. The second one as well from China. Then the third one is from Europe, Pisdane. And the fourth from Japan. The first one from United States is the fifth in the list. So, well, in general, there is a very global race to achieve Xscale. That is the next target. So we have 125 petaflops now in a supercomputer. We want to achieve 1,000 petaflops. That would be 1 exaflop. And this is like a global race to achieve this objective. And there is a lot of countries pushing for this, and China is one of the countries that is putting more money on this. Also, Europe has a lot of investment on supercomputers. The proof is that Mare Nostrum supercomputer. And for instance, one of the contracts that is one of the agreements of the Commission is to invest 1,000 million euros in achieving the scale in the following years. So HPC matters for the because that's why countries are investing on this. It matters for competitiveness and in general of countries. Here we see the top 500 list in another, the Moore's law trend in another way. Here we see the performance of a single thread. So the sequential performance, it increased following the Moore's law until 2004, more or less. So that meant that without doing any change in our codes, we could multiply our performance year by year, right? Just because the frequency could increase and the sequential performance of the cores increased. This stopped, the performance, the sequential performance stopped around 2004. Well, then it kept increasing, but not so fast. And what happened is that we started to have parallel chips with more than one core. And that's why, that's the way that we could keep increasing the performance of the supercomputers, by increasing the number of cores per chip, right? So that's where it started the parallel programming within the nodes. The multi-core era, sorry. So this is the general trend, more slow, the evolution of supercomputers. But it's not, there are two things when we carry out a simulation. One is the arithmetical operations that we see that the performance is increasing year by year without stopping. The other part is moving data from the memory to the registers in order to carry out the operations. And the bandwidth, this is the bandwidth of the system. The increase of the performance in the memory, it's much lower than on the capacity of performing floating point operations. So what does it mean? That year by year, the limitation is becoming more on the memory side than on the operations, right? On the computations, because so you need to carry out a simulation, you need to move data to the chip and then carry out the computations. But this transfer of data is getting more and more slower in comparison with the computations. So we will need to wait for data to arrive to the chips in order to carry out the computations. This is referred as the memory wall. In order to reduce this difference between the increase on the memory speed and the computational speed, what chips do, what the design of the CPUs, what they do is a hierarchical strategy between the main memory, the RAM memory, and the processing units. There are different memories named cache memories to store data, and these memories are smaller but faster. So the information can go faster from these memories to the processing units. The cache memory on the chips, it's of the order of kilobytes. This is in the same chip where you have the processing units, and the time is it's of the order of nanoseconds, 1 nanosecond. Then when you go to the second level of cache, which is outside the chip, you have the sizes of the order of megabytes, and you have one order of magnitude more in terms of costs. Then you go to the main memory, and you have a size of gigabytes, but another order of magnitude in the cost of the transfers. So when we carry out simulations, we move from the main memory to the. So this is the last level of memory that we use. We generally don't go to disk for the operations, only to store data, but not to carry out operations. So we move from the main memory to the computing units and storing data in the cache. So what do? We try to exploit locality. When we move data from the main memory to the cache, or from the second level of cache to the first level of cache, this moved in packs, in blocks, or words, it's also called. So what you try to do is to store data that you are using consecutively in the program, or also store it consecutively in the memory. That's in this way, when you move a pack of data, a group of bytes from the main memory to the cache, probably you will get there data that you are using later in the same calculation. This is referred as spatial locality. So store data together, the data you are using consecutively, store it together in memory. So this way you you can use the same data that you have moved. The second locality that we are trying to exploit is temporal locality. So when you are trying to use the same data, so that when you use some data, it's kept on the cache while there is a space on the cache. If you have to reuse this data later, try to use it before this is removed from the cache, because other data is moved to the cache. So try to exploit temporal locality as well. So keep the data together in memory and try to reuse data as soon as possible, so this way it will be in the cache. Okay? This is very important, locality. Try to design your program so that you use the memory in a smart way. This is there is a concept that is very important nowadays on parallel programming and in general high performance computing. It's the arithmetic intensity of your algorithms. The arithmetic intensity is the number of the work or the number of operations, the floating point operations that you do per byte that you are moving from the main memory to the cache. So the higher is the arithmetic intensity of your algorithm, the less that you will be limited by the memory wall, right? There is a peak performance of a device. Here I note it as tau. And there is a bandwidth. The bandwidth is the speed in which the data is transferred from the main memory to the cache. When your algorithm, the arithmetic intensity of your algorithm corresponds to the peak performance divided by the bandwidth, that means that you are in like an equilibrium point. So in the same velocity that the data is moved from the main memory to the cache, is consumed by the computing units, right? When your arithmetic intensity is higher than this, that means you will be compute bound, because you will have to do computations with data that is already there, so you don't have to wait for data to come, because you have more computations than data transfers, right? So you are compute bound. When you have a lower arithmetic intensity, of course you will be limited by the memory. So you have few operations per byte moved. In general, the time of computation is very small compared to the time of data transfer. So most of the time you are waiting for data moving from the main memory to the cache. This is, in general, our most of applications are memory bound nowadays. I will show you some more information about this later. All the linear algebra, computational linear algebra in general for sparse matrices is limited by memory, not by computations. Here we see a trend of different kind of devices. For instance, Intel Xeon in blue. This is how the performance increases on time. And this is how the bandwidth of memory bandwidth has been increased until 2016. So we see that the computing performance is increasing much faster than the memory bandwidth. That means that the equilibrium point when you are achieving all the performance, so the arithmetic intensity that you need to achieve all the performance of the device is increasing. Nowadays, or on 2016, to achieve all the performance with an Intel Xeon CPU, you need 80, let me see, 10 flops per byte. Yeah, this is in flops. 10 flops per byte. So as one double precision variable, it's 8 bytes. This means that you need 80 flops per each double precision node that you are moving to the main memory. So in general, the idea is that we are limited by memory transfers, right? And this trend is increasing. So computing is improving faster than memory transfers. This is another example of this idea. This is linear combination of two vectors, this operation. Then we have matrix vector product and product of two matrices. There are some standard libraries called BLAS, right, that implement these operations, so they can be used on any system. BLAS level 1 is for the linear combination of vectors. BLAS level 2 is product of a matrix by a vector, and BLAS level 3 is product of two matrices. We see that the performance of this is a Intel CPU from 2007, I think. Well, we see that the performance that we can achieve from the linear, for the two first level of the BLAS library for the linear algebra operations, it's only 3 and 6% of the device. It's very low. So if you want to do the summation of two vectors or do a matrix vector product in a CPU, Intel CPU, in general the performance, the part of the peak that you will achieve, it's around between 3 and 6%, right? If you do sparse computations, this is for dense matrices. When you have sparse computations, this means that you have random memory accesses. It's less regular. It will be even worse than this. When you do matrix-matrix vector product, you can achieve almost the peak, right? I don't have the percentage here, but so supercomputers are evaluated with these kind of operations, but there are many applications which are based on this kind of operations, on matrix vector product and on a sparse linear algebra, etc. So you see that we can achieve a low percentage of the peak. Question, yeah, thanks. BLAS is basic linear algebra, basic linear algebra subroutines. It's like a standard, and it has different optimized implementations on different systems. Most of vendors have their own implementation and optimized for specific devices.
Okay, but then again, what are the different levels? Or how does it? How can there be different levels of processing?
Depending on the operations, these are classified in levels. BLAS level 1, it's a linear combination of vectors. X equal to a scalar by another vector y. Then second level, it's matrix vector product, dense matrix vector product. And the third level will be the product of two dense matrices.
And the intensity is how much it
Is increasing.
the lower the intensity, the more demanding it is?
The more?
The more demanding it is on the computer's resources, or the less efficient?
Can you repeat? The higher the arithmetic intensity.
The lower the I, the intensity,
Mhm.
the less efficient it is, right?
Yeah.
And so, and you said that when you combine two matrices, so last three,
BLAS 3 is not combination, it's do the operations. For instance, a sparse matrix by a vector, you have to random memory accesses to the vector according to the entries, but it's not sequential, the access to the vector. So that's then, if depending on how is the data stored, you have to move much more data than need. So that's where the intensity, the arithmetic intensity in practice, it gets lower, because you move more data than you need for the operations.
well, I can tell you that a lot of faculty members in this university at UPC here think that sparse matrix product is more efficient and faster.
It's more, of course, it's more efficient. It's more efficient and faster than performing the dense matrix, because you are storing a lot of zeros that are not needed, right? But the speed that you achieve, the operations per second that you achieve when you are multiplying a sparse matrix by a vector is lower than when you are multiplying a dense matrix by a vector. However, when you multiply a dense matrix by a vector, most of operations are not needed because are zeros. So you will be faster with the sparse matrix. So, but the idea is that memory transfer, it's one of the most important things in your applications, because you are limited most of the time by memory transfers. Because the speed of computations is very fast, you don't care about it. You move data, it's for free, more computations in many parts of your application, right? So, yeah, I am finishing this part. If we see this is the top 500 list again, and here is the part of the peak of the supercomputer that is being achieved when running the Lean Pack benchmark. The impact benchmark is the benchmark that is used to rank the systems. So they are very efficient running the impact benchmark. But if we run the sparse computations, you know about CG algorithm, it's a sparse solver, or it's the solution of a sparse system, right? The systems are much less efficient. So we see that the number one system in the world, some way, according to impact benchmark, would be the number 3 in the world, according to this other benchmark, based on a sparse linear algebra, and only 0.3 of the peak performance of the system is achieved, right? But a very important part of computational mechanics applications rely on sparse linear algebra, right? So we are achieving these parts of the peak performance of the system. Okay. Now we will give some ideas on Xscale. Xscale, as I said, is the next objective on supercomputing. We want to get Xscale in the following years, in the 2020 something. We have seen that the number one system in the world spends 15 megabytes and it has its performance is 125. Sorry, there is a mistake. It's petaflops, not flops. So to achieve Xscale, it's 1 order of magnitude more. The energy consumed will be, if we do solve this very easy problem, 150 megabytes. So only with the same technology that we are using today to achieve Xscale performance, so it will require 150 megabytes per year only on energy consumption. So these are around 150 million euros only spent on energy consumption. So this has pushed a lot of research on energy efficiency on supercomputers. There is another ranking which is called the 500, the Green 500 list, that it ranks the supercomputers in terms of energy consumption. And well, we have to say that the consumption of the supercomputers is the watts per flop or the flops per watt are increasing exponentially. So there is a lot of research and focus on improving the energy consumption of supercomputers. Okay, so this is the general trend of HPC. Now I will show you a little bit of Alia. That is the code that we are developing in our department, in the case department. So it's a code to run on supercomputers. It's a multiphysics for multiphysics applications, and it's divided in different modules depending on the application. So there is transversal development in Alia. We are developing meshes, numerical methods, turbulence models, multiphysics coupling, HPC optimization, etc. And this same kernel is used in different applications on energy, biomechanics, hydrodynamics, industrial flows, etc. And this is the team that is developing our software. I think Mariano did a talk this morning. I am in the HPC team, so in improving Alia to achieve performance on high-end supercomputers. And well, this I skip. If we see the millions of CPU hours that we spent on 2016, this is 2 years ago, it's around 31 million CPU hours that we spent running Alia system on different supercomputers. So it's quite a lot. This year it has been, last year, 2017, has been much more than this, because we had the highest or the largest HPC project that you can get in Europe. It's the PRAISE projects, and you get around 20 million CPU hours to run these projects. Well, this year we got 2, so we are going higher than this. Okay. So Alia, if we see the anatomy of a simulation with Alia, it has mainly three parts. It's the pre-processing part, where you have the geometry, and you do some meshing, so you have to discretize the geometry. Then there is the simulation, the process. The process, it's mainly a loop between the assembly of the equations, but on each time step, you have to assemble the equations, run a linear solver to solve the equations, and then repeat again, right? And you follow a time integration process where the equations keep changing, and you have to solve them on each time step. You also do some output during this time integration process, and at the end, when the simulation is finished, you do some visualization of the results, right? So we want to be parallel for all these steps on the pre-processing, on the post-processing, and on the time integration, on the process and the post-processing. Here I show you a video. I don't know if you have seen this morning, this video. This is some visualization for simulation of the flow inside the respiratory system. I don't know if has Mariano shown you this video? Okay, we use, so here we are simulating the flow inside the respiratory system, and we are tracking some particles. The idea of this simulation is to see the deposition of the particles in different parts of the respiratory system. We work with some companies for these kind of simulations are of interest of different companies, of different inhalation systems, etc., to study depositions and all these things. And well, this is a very nice visualization, I guess.
What is you tracking the gas or particles?
Particles that are, so we are simulating the flow and how the particles are transported.
Are you simulating the interaction of the gas and the particle, or just the flow of and the shape of the particle can influence?
No, here I think there is just there is not interaction between the flow and the particles. That's we study some depositions of particles in different parts. Okay.
And this is all linear, laminar?
No, there are some turbulent. A turbulent model is used for this. Yeah, there are turbulence also too.
It looks laminar. Just looking at it.
It's laminar, but well, I'm not expert on this flow, but I know what I listen from people that is running these simulations, that they have to use some models for turbulence. I don't know in which specific part the turbulence is being generated, but
The entry
probably in the entry, yeah. And about the interaction of flow and particles, I'm not sure if there is. Well, they are coupled, so probably if there is interaction, it's being simulated as well. So it's not that the flow is simulated first and then we inject the particles; they are simulated together. Okay. So I have given a general introduction of HPC trends, also a general introduction of what is Alia. Now we'll talk about parallel programming, the different levels of parallelism in a supercomputer, and how they are reflected in our code, right? So the first, first some concepts. So some metrics that we are using when we are evaluating the performance of our code. One of the most important ones is the strongest speed up. The strongest speed up is the acceleration of your code. So you start running your code with 100 CPUs. You want to go faster. You go to 1,000 CPUs. So you expect to go 10 times faster. So this is what we measure: the time with one number of CPUs divided by the time with another number of CPUs, larger number, and ideally you expect to achieve the result, the ratio between the two number of CPUs that you are using. And the other metric that we are using also is the weak speed up. The weak speed up, what measures is if you increase proportionally the size of the problem and the number of CPUs and the number of resources, how much the time is increasing or decreasing, in general increasing. So ideally, you expect that if you increase the size of the problem and the computing resources proportionally, the time will be maintained. This is another kind of measure that we are using, right? This referred as weak speed up. So here we see some tests of Alia in different supercomputers from different countries as well. I think that the larger test here is the test that we carried out in Blue Waters. It's around 100,000 CPUs that were used. And we see that we achieve a quite good, strong speed up. I think the initial point was with 32,000 CPU cores, and we doubled the number of CPUs 2 times, and the performance was quite good. So in general, the simulation that we do nowadays, it's in the order of thousands. In some cases, we use, for instance, we are running some simulations of a plane, which are quite expensive. We run them on 12,000 CPU cores, right? Other important concepts or principles of parallel programming, well, the Amdahl's law that says that, well, if there is only one part of your code that can be, so when you do you have to see which part of the code you are accelerating. If, for instance, if you have a code and only half of the computation can be accelerated, doesn't matter the number of resources that you use, you can only go 2 times faster. Because if there is a part that is sequential in your code, this cannot be accelerated. Doesn't matter the number of resources that you use. So this is important to check, to see which part of your algorithm, you have to always focus on the part of the algorithm that takes more time, more percentage of time, and accelerate that part. Granularity, locality, as I said, it's very important to take into account memory locality when you are programming to minimize memory transfers. Granularity means the partition of your problem. When you parallelize your problem, you have to decide the size of each part, right? I will show you more about this later. Load balancing is very important. So you are running a simulation with 1,000 CPUs. You need that all of them take the same time. If there is one CPU that goes as one CPU or one part of the problem that it takes more time than the others, at the end all the other CPUs will be waiting for that to finish. So and you will waste a lot of resources. So load balance is very important. Then the communications between processes, you have to minimize them, and synchronizations because they are expensive. And you have to take into account all the costs that. So you have to take into account all the costs when you design an algorithm, you have to take into account all the costs that all the operations have on the system. You have to include this in your model. If you know that the communications are expensive, the design of your algorithm must take this into account. Or you know that the data transfers are expensive in your case. All these aspects of the hardware must be reflected on the design of your algorithms. So you need a good idea of you need to have a good idea of how is the hardware performing. Okay, another way that you use to measure performance is doing what is called as traces. Here we see a simulation. Each line corresponds to a computing unit, a CPU. And the different colors are different types of operation. There are communication is the blue part. Then communication is the yellow part. The point-to-point communications. This means communication between different processes, but one to the other, not global. And then there are also global communications. In general, global communications derive in a synchronization of the simulation, right? When, for instance, there is when you need to evaluate a scalar product between 2 vectors. So you have a vector, you need one value derived from the from the scalar product of two vectors. This results in a synchronization of the code at that point. You have to sum up all the values from all the CPUs. So you have synchronizations coming from the global communications. So there are some softwares that we use to analyze the code to see, for instance, here we see a huge load imbalance. There is computation for one CPU that is much longer than for the others, and this produces a lot of idle time because these communications, this yellow part, these communications in fact are not expensive. You see other communications here that take very short, but what is happening is that a lot of CPUs, the other CPUs are waiting for the messages from this CPU. So there is some idle time produced in this communication, or in the global communication. So this is another kind of analysis that we do to ensure the performance of our code, right? We measure the acceleration, we measure the time, so we need that the code accelerates, that the code is fast, which are two different things. And we also need to take care of imbalances, etc. Yes, thanks.
The long orange and yellow line, is it idling of the CPU, or why is it communicating so much? So is it waiting in the middle?
Okay.
For some CPU?
What's happening here? Blue is computation. So it's what we see here, that this guy is taking much more time than the others. Then there is yellow, that is a point-to-point communication. And after this, it's a little bit difficult to see. There is an orange communication. It's a collective. The collective communication, or the global communication, synchronizes all the cores. So this means that all of this, here there is a synchronization point due to the collective, the global communication. As well, there are some. So here it also happens. Let me see. There must be some other cores that are waiting for data arriving from this core. That's the cause of the yellow part. So at the end, it's communications can produce idle times on the receiver when the sender is not delivering the data on time. So this guy is waiting, has arrived on the communication much before than the sender has arrived to the communication, so it's waiting a lot of time to this communication to complete. So that's what is happening. Yeah. So we do this kind of analysis also to check that our code is performing properly. Okay, so I have tell you some basic principles on parallel programming, some metrics that we use, some analysis. Now let's see which different levels of parallelism that coexist in a supercomputer. The first level of parallelism is within the CPU, right? The CPUs, what they do is they use pipelining. This is on the compiler level, so we don't do anything on the code to improve this. But what does the CPU, it's break one task in different phases. So this way, they can be performed simultaneously the same phase of different tasks. Or different phase. How is this? The different tasks can perform different phases on the same time. For instance, let's see a very simple example. So if you have to do a laundry, you have wash, dry, and fold, right? These are three phases for a task. You don't need to finish one laundry before starting another laundry. So you can do different parts of the laundry for different clients, let's say, at the same time. You can wash and dry and fold 3 on the same time, right? So the performance that you achieve by doing the pipelining, it's proportion. It can be the potential speed up is the number of stages. Here, to do a laundry. Well, in this example, it's for 4 laundries. If you do one after the other, it would take 6 hours. If you do the pipelining, it would take 3.5 hours, right? So this is the same principle. It's applied on CPUs internally at the instruction level to increase the. Well, this is an example for the fused multiplication addition. Fused multiplication addition is an operation that instruction that is carrying out a multiplication and addition at the same time, right? And it has 5 cycles. So it's divided in 5 parts. When you can run 5 instructions of this at the same time, you see that the performance that is being achieved is 5 times higher than the performance when you only run one. So the pipelining accelerates your computations. So this is the first level of parallelism. There is a parallelism inside one single core. The second level of parallelism is the vectorization. Vectorization, it's instead of doing one, for instance, in this example, instead of doing one addition of 2 numbers, you can do one addition of different numbers at the same time. So we have 2 arrays of 4 real values, and we can do the addition of all of them together. This is vectorization, right? Instead of doing a scalar operation, you do vector operations. So that you manage data within vectors. The program that has this, so you are accelerating this way the computation, but at some point when the size of the data is at some point the size of data is too large, you are paying again what is killing your performance is the transfer between main memory and cache, right? But well, this is another possible parallelization within a single core. And this, we are applying this in Analia. So we are vectorizing our code when you carry out the assembly of the linear system on each time step. So we group the data in vectors of a specific size. For instance, here we see vectors of size 4. Well, this has 3 steps. First, you gather information in vectors, then you carry out the computations, and finally you scatter the data, again on the global system, let's say. And well, this requires some modifications in the code to carry out vector operations instead of scalar operations. And here we see some example of the speed up that we achieve doing this. It's around, we reduced the time by around 6.5, so the time is reduced by 6.5 times. So performing vectorization is a way to accelerate your code, to accelerate operations. And this was done in a KNL device, running this simulation of a flow around a sphere. Okay, so we have seen the 2 strategies to achieve parallelism or within a chip, within the chip. That's pipelining and vectorization. And then let's see the InterCPU parallelism. So parallelism that we are achieving when we are using more than one CPU. So this can be divided in 2 types. There is the shared memory space. That's when you run different cores, when you run a simulation within a node, where all the cores have access to the memory, right? The second, so when all the computing units have access to the same memory space, right? This will be shared memory. And the second the second paradigm is the distributed memory. So supercomputers are divided in nodes, right? And they are connected by a network. The cores or the CPUs of a node have not access to the memory of another they have not access to the memory of another node. And then the communications are required through the network. So we have the shared memory and the distributed memory. And then, well, there is also, I will talk a little bit of GPUs. So the idea of shared memory is that there is a common memory for all the computing units, the processors, 1 to n. There is a shared memory and a bus to transfer data between the memory and the computing units. So different processes have access to the same memory. The main library that we use to program our algorithms in shared memory is the OpenMP library. I will show you an example. Let's see a very simple example, the calculation of the number pi. So this can be done with an integral of a part of the sphere. And this can be done with a summation, a discrete integral. So this is a summation. You have to evaluate the function and multiply by a size of the. So you have to divide this area in rectangles. For each rectangle, you have to evaluate the function and multiply by this size. And you have the area of this rectangle. If you sum up the area of all the rectangles, you have the area of this function, right? This is a discrete integral. The thinner it's, the larger is the discretization, the more precise will be the result. So here we see a program to carry out this discrete integral. Well, it's very easy. It's a for loop. You have to evaluate the step. The step is the size that you will advance from one your discretization step. And so you have to do a loop, and evaluate the function, and multiply by the size of the step, and you then get the number of you can get the result of p. So the numerical integral of this function. So how would we do this in parallel? So doing in parallel, in shared memory, parallel computations, the idea is to, we use the fork and join paradigm. So we have a loop. So this integral, this summation is carried out through a loop, a for loop. And what we do is that we divide this for loop so that each process will do a part of the iterations, right? So it's as easy as before the for loop, you put a pragma, OpenMP parallel, and this means that each parallel process will do, this for loop is broken in different parts, and each parallel process will compute one of the parts. There are some important things that, for instance, so here you are doing a for loop. In each iteration, you are evaluating the area of the corresponding rectangle, and then you have a global variable where you accumulate the summation. So you have different parallel processes carrying out this summation. All of them accumulate on the same variable. You can have race conditions. That means that you can access to this unknown. All of the parallel processes have to access to this unknown at the same time, and this can produce some errors. So you have to get sure that not two parallel processes get access to this unknown at the same time. And this is just putting you have to add this option that say that you are doing a reduction into this variable, right, to avoid race conditions. So shared memory is very simple, but you have to take into account different aspects. Like two parallel processes writing in the same unknown at the same time can produce errors, so you have to take into account these aspects. So now I will show you how we implement parallel the shared memory within Analia. So, as I said when we have access to the same, we are writing. So when we have a mesh, we have a field defined on a mesh, and you have an unknown corresponding to each node, right, of the mesh. And we are writing values on the nodes corresponding to each vertex or to each node of the mesh. But there are problems when we have two parallel processes writing in the same unknown. When we do a parallel execution of our problem within a shared memory space, what does it mean? That there will be different CPUs running different parts of the simulation, right? The division is only on the mesh. So different CPUs will account for the integration on different parts of the mesh. But on the boundaries of each subdomain, it happens that two threads or two CPUs access the same node, one to write on the same node. And this has to be avoided, and we use what is called atomics, the same that we used before the reduction, the set as I said you before with the example of the integration of pi. So this requires atomics. We have to take into account these problems. To do this, we use some coloring strategies, that is, perform only the operations for elements that are not, so we only can perform operations between elements that are not neighbors, so we avoid this problem. This is the coloring strategy. Then we have another strategy based on partitioning and having an interface between the subdomains that avoids this, and we treat the interface also later. And finally, we have another strategy based on task parallelism. So we have, so it's more or less complex, this. But so shared memory is not as simple as it seems, right? So we have to take into account these race conditions, and to achieve performance, there are different strategies. I think it's better I don't go into details because each of these strategies has its own problematic. For instance, when you use vectorization, you are losing locality because then you will follow, one parallel process will access to data that is not, so data is accessed, but they are not in the same, they are not close to the other, so we lose locality, right? And well, there are different aspects here that I think it will be difficult to explain here. This is the implementation of these strategies. I think I'm not going to details. So, right, we have seen that there are different levels of parallelism. There is the parallelism within a core, which is, there is pipelining and vectorization. Parallelism within a shared memory space, so within nodes of a supercomputer. Supercomputers are divided in nodes. Within a node, all the cores have access to the same memory. Shared memory paradigm. And then we have distributed memory paradigm, that is when we have to run a program that will use different nodes. Here, different parallel processes don't have access to the same memory space, so we need to use communication. This is illustrated in this image. So we have different processing units. Each processing unit has its own memory space, and to access to data that is stored in other processing units, we need to go through the network, right? So maybe I don't know if this is clear, but so the way that we divide, so we have the problem, right? A problem has a initial phase that is a geometry. We do a maze discretization. Then we want to run it and post-processing. In order to divide the problem between different parallel processes, to run in parallel, what we do is to divide the mesh. So the decomposition of the domain, the parallelization is associated to the decomposition of the domain. So we do a partition, mesh partition, right? What happens? That all the elements that, so we are solving a discrete equations on each element of the mesh. These discrete equations relate each element with the boundary elements, right? When we assemble these equations and then we solve the linear problem associated with these equations. So in the boundaries of the subdomains, what happens? That you are related, your element has relation with elements in other subdomains. So this subdomain corresponds to one process, this other subdomain corresponds to another process, so you need access to data that it's associated with another process. When we have, in the distributed memory paradigm, we don't have access directly to this data, and then we use communication. Communication, it's the main library used for communication, it's called MPI. And we use some operations that there is an MPI send, MPI receive, MPI wait all, that means stop until the communication is finished, etc. So any kind of, we also use synchronization operations, etc. Right? There are different types or modes of communication. We have asynchronous communication, synchronous communication, blocking communication, non-blocking communication. So there are different strategies. Each one must be, we have to take care which one is being used on each part of our code.
What's the best documentation source for
MPI? The main page of MPI, I don't know which domain it is, but probably you will find, yeah. And there is MPI 1, MPI 2. So this is standard. It's updated each 3-4 years, I don't know. And so it's on a standard and says which operations must be supported. And then there are different implementations, right? It's on a standard that says which operations need to be. Yeah, there are many operations in different level of detail, but the idea is that you transfer data. So shared memory, you don't transfer data explicitly. In distributed memory, you don't have access to the data because it's in another memory space. So you transfer data between processes, right? So I haven't gone into details, but because I think it's not very exciting for you. But so more or less I have explained you the 3 levels of parallelisms: intranode, shared memory space, and distributed memory. Then there is other things, important things that, for instance, mesh partitioning. There are different strategies for mesh partitioning. So the mesh partitioning is that when you do the mesh partitioning, you are decomposing your problem to run it in parallel, right? There are strategies based on graphs. So one mesh it's composed of elements. Each element has a connectivity with the neighboring elements. This can be expressed in a graph. And you can then divide this graph trying to minimize communication, trying to minimize the communication requirements associated with this partition, right? There is the graph strategies. There are also geometric approaches. That means it's another way of partitioning meshes based on what is known as space filling curves. So what you do is you transfer the domain following a specific order, and what you do is you accumulate elements while you are traversing the domain. When you have an objective weight, you cut, and then you start another domain. So it's a geometric approach, not a topological approach. It has some advantages, can be more, and some specific curves are used. These are referred as space filling curves that try to preserve locality. So elements that are near in the curve are also near in the space, right? Preservation of locality. Well, we have developed some strategies on this. We are able to, for instance, this is an example for a 17 million mesh. We can divide it into 4,096 parts using 4,096 processes as well in only 3 cents of second, 4 cents of second, right? So it's very fast, it can be very fast. And this is a specific implementation that we have developed and published, etc. And now we are using it. So dividing a mesh, one of the requirements is that you, the partition that you carry out gives you a good load balance, right? So when you are performing the calculations on the different parts of the domain that you have carried out, the cost of the computation will be the same per each part. This is not straightforward because it's not clear which is the cost of each element when you carry out the computation. It depends on many things. It depends on the type of element, it depends on how is stored in memory, the locality, on the loop that you will do when you traverse the elements on this part, etc., etc. So what we have been developing now is a strategy for dynamic load balancing based on geometric partitioning. Well, this is the result. This is an initial imbalance. So these are 200 cores, 200 CPUs that are used for a simulation. And this is the time on a specific phase of the simulation, the time that takes each CPU. So we see that it's not well balanced. And using a specific strategy based on geometric partition that we have developed, we see that we achieve a very good balance after this process. We also have other strategies for load balancing. It's an important problem. There is a library developed here in Barcelona Supercomputing Center called DLB. That what it does, when there are idle times means that there are some specific CPUs that have nothing to do, are waiting for instance, the communication to complete. So are waiting for data to arrive. So they have nothing to do at that moment. So within the shared memory space, some work is transferred to these CPUs that are idle at a specific moment. So this is illustrated here. This is another strategy to improve the load balance on simulations. Finally, I will give some basic idea on GPU. So this is GPUs are being used for computations from some years ago, and one of the reasons is because they are the ratio between flops and buds it's higher, so they are more energy efficient. So they are an alternative that is being used more and more on HPC. There is a very important difference between a CPU and a GPU. This would be a diagram or for a CPU. We see that you have the computing units, and a lot of space on the die is occupied by cache memories to try to minimize the memory. So try to keep data close to the computing units. The GPU is another design. So this is a latency approach. Tries to minimize the cost of one single computation by trying to store all the data as close as possible to the computing units. The GPU follows another design principle. It's called throughput-oriented approach. This means that what we try to do is to run a lot of computation at the same time, and we try to hide the cost of data transfers by switching between different computations that are in a queue, right? So we have here we try to have all data ready for a single computation. On a GPU, we have a lot of computations running simultaneously, and we hide the cost of transfer of memory of data transfers by switching between one computation and another. It's another principle, right? Well, I had some results on GPUs. Question?
The right one should be GPU. So
Yeah, this is GPU.
because they're standing CPU design goals for GPU even wrong.
Yeah, this is wrong. This is GPU. Yeah.
Yeah, okay.
Yeah, it's wrong. This is GPU, this is CPU, right? So CPU, small part of that is it's occupied by computing units. On the GPU, most of the die, it's occupied by computing units. There are two design. The design is completely different. So here the idea is throughput. Here the idea is a single thread going very fast. Here's a lot of threads performing a lot of work at the same time. There are two. This is illustrated on this example, for instance. This is a sparse matrix vector product. The performance in gigaflops that we are achieving at running a sparse matrix vector product. When we increase the size of the problem, we lose locality, so the performance goes down when we run on a CPU. On the contrary, when we run on a GPU, when we increase the size of the problem, the performance goes up, because there is more occupancy on the GPU and more chances of switching between different threads that are running simultaneously. So we better hide the memory costs. Good.
Does Amdahl's law still hold somehow, or
What?
you had at the beginning Amdahl's law, like
Yeah.
problem. Is it still holding, or is it?
No. This is so here we are analyzing not a problem with different parts, where Adam's law what said is that you have to focus on the more time-consuming part, don't focus on the details. This is what it says basically. Here there is not a problem with different. It's a sparse matrix vector product. We want to accelerate this part, right? So it's a sparse matrix vector product. What I want to show with this result is that performance of CPU in terms of arithmetic operations per second, when it's a small problem, what happens? It fits within the cache, and the memory transfers are faster. So the memory limitation is not showing here. You have more performance. As you increase the problem, not all your problem will fit in the cache. You will have to go to the main memory, and you are losing. You are doing less operations per second. You have delays because of memory transfers, right? This is what happens on the CPUs. On the GPUs, it's another principle. The more work you have, what you do is, for each row of the matrix, you use a thread. So you throw a thread to the GPU, like a job to do. So you have a lot of threads running at the same time simultaneously. When one thread is waiting for the data to arrive to the registers, another thread is executing. So it's switching from one different context, you say. So you increase the problem, you increase the performance.
But then it's true. It's not anymore Amdahl's law somehow. If you increase the size, it's not that.
Amdahl's law is so. When I say increase the size, I mean solve so here what we are doing is sparse matrix vector product. A by x equal to y. Sparse matrix vector product. When I say increase the problem, it's increase the size of the matrix. This could be another problem like the addition of two vectors. Doesn't matter. In general, in the GPU, you need the occupancy of the device in order to be able to hide latencies, to hide the memory transfers by switching from one thread to another. Adam's law is when you have a simulation, for instance, you have an Analia simulation of the respiratory system. And you have a preprocessing, time integration, post-processing, I/O operations, and you focus on the parallel performance of the assembly part, the matrix assembly part, which is one of the parts of the simulation. But if the assembly part only takes 10% of the overall simulation, Adam's law, it's a very common sense. It says, don't focus on this part. Focus on the part that takes more time. For instance, the solution of the linear system. So but here, I'm solving one specific problem. I'm changing the size of the problem and see what happens. This relates with the different types of device and design models. I think I have given a lot of information. Maybe it's far from you, or maybe, but well, maybe you keep something also. Well, these are some speed up results. This is the same that I showed you in the previous slide. When you increase the size of the problem well, it's another way of seeing it. I have already said it. Maybe better not to go into details on this. And well, we are on Analia. We are trying to run on GPUs and CPUs at the same time. We call it the co-execution strategy. Well, we are using also the load balancing library that I said you before, because some cores will download its work to the GPU, to accelerators. These cores mean that they are not being used, and we use DLB to share resources between within the node. Well, it's a way to try to achieve the maximum occupancy and maximum use of all the resources. Right? So this is the last slide, and just it shows some simulation of an airplane. I think this simulation is the one I told you before. This specifically is using 6,000 CPU cores to perform the simulation. It has quite a lot of details on all the turbulent flow, etc. And that's it.
What do the colors refer to? Pressure?
I guess so, yeah. It's vorticity, I think.
This is really bad.
I don't know the angle of attack, right? So
This is really bad.
the specific angle of attack, it will explain the results.
It's very surprising.
Well, I just put it as an illustrative example of what we run in Analia. I think the mesh the discretization that we are using here is around 300 million elements mesh, more or less.
Well, it depends on so many things.
Yeah, it depends on so many things. Speed, angle of attack. Yeah.
Everything, so.
Yeah. It's illustrative result, not. So, do you have any question, comment? If not, you have some question? So thank you.